Good day everyone, my name is Rebenting Flores and for today we will discuss about multiple integrals, specifically the triple integrals. So triple integrals is defined in a similar manner to that of the double integral. F of x, y, and z is a continuous and single-valued function of x, y, and z all over the region R of space enclosed by the surface S. We subdivided the region R into rectangular cells by planes parallel to the three coordinates planes in figure 1 as shown in follows. The parallelepiped cells may have the dimensions of the partial integral of x, partial integral of y, partial integral of z. We number the cells inside R as partial integral of v1, partial integral of v2, up to so on until we came up with this the partial integral of b sub n or n. In Fovini's theorem for triple integrals, if f is continuous on the rectangular box B is equal to the bracket of AB multiplied to the bracket of CD multiplied to the bracket of RS. Then we came up with the triple integral, the function of x, y, z dv evaluated to the limit of b is equal to the triple integrals of the function of x, y, and z dx, dy, and dz evaluated from for dx we have ab, for dy we have cd, dz we have rs. The volume of a, which is the volume of a, is equal to the triple integrals of dv evaluated to the elements of a, limits of a. Evaluate the triple integral of xyz squared dv from b, where b is the rectangular box. We have this rectangular box. This is the representation of the limits to be considered in integrating the triple integral. So we came up with xyz. For x we have 0 to 1, for y we have negative 1 to 2, for z we have 0 to 3. Solution. We could use any of the 6 possible orders of integration, integrate with respect to x, then y, and then z, and then we obtain this, the triple integral of xyz squared dv, and then substitute the following limits or the box of b, rectangular box. So we came up with xyz squared dx 0 to 1, dy negative 1 to 2, dz 0 to 3 is equal to the integral of the first limits of dx. We came up with the remaining two integral of x squared y z squared all over 2 evaluated from 0 to 1 dy dz. So we came up with the remaining two integral this y z squared all over 2 dy dz is equal to, if we integrate that to the limits of dy, so we came up with the last remaining integral of dz evaluated to 0 to 3 is y squared z squared all over 4. Substitute the value of negative 1 and 2, so we came up with 3z squared all over 4 dz. Evaluate that with the last limit, so we came up with 3 all over 4 evaluated to 0 to 3, and that will be equal to 27 all over 4. Next is evaluate the three integrals of a z dv, where a is the solid tetrahedron bounded by the four planes. X is equal to 0, y is equal to 0, z is equal to 0, and x plus y plus z is equal to 1. So we have this rectangular or tetrahedron of A. We came up with x, y, z. For x, we have 0 to 1, y 0 to 1, and for x is we have z, rather we have for y we have 0 to 1 minus x. For z we have 0 to 1 minus x minus y. As you observe in the association, that would be the tetrahedron. So we have the particular limits of 0, 0, 1, 0, 1, 0, 1, 0, 0. So we came up with a solution. Then triple integral of z dv is equal to the limits of z dz is 0 to 1 minus x minus y. For dy we have 0 to 1 minus x. For dx is we have 0 to 1. Simplify z given the integrate z with the particular limits of 0 minus 2 1 minus x minus y. So we came up with z squared all over 2 dy, and then simplify we came up with 1 half then two remaining integral 1 minus x minus y square dy, and then integrate that with the dy, the limits of dy. So we came up with 1 over half 1 over 2 0, and the integral of negative 1 minus x minus y cube all over 3, limits of 0 1 minus x dx evaluated from 0 to 1. So we came up with 1 6, the remaining integral 1 minus x cube dx, and then simplify or integrate that with the limit of 0 to 1. So we came up with 1 6 minus 1 minus x raised to 4 all over 4 diluted from 0 to 1. So we came up with the value of 1 all over 24. And that will be all. Thank you. Bye bye.